Okay, so we're going to look at a couple acid-based questions. We're not given any pKa tables, but we are given just the structure, and we want to know to which side the equilibrium lies. Is it going to be left or is it going to be right? And so even without a pK, we are able to discern which side the equilibrium favors. So if we just recall what kind of factors we take in, we want to look at who's holding the charge, or well, if there's, sorry. We also, let's look at these factors here to consider. Number one, is there any charge? And if so, who's holding the charge? Or if not, then, if there isn't any side that's holding the charge, then it will be more stable, right? Because charges bring instability. But if there is a charge, then we want to know who is holding the charge and if it's good, right? We also want to know if there's resonance involved in stabilizing that charge. We also want to know the hybridization. And recall that if you have a hybridized sp orbital or maybe an sp3, the hybridization stability goes to sp, sp2, sp3, sp3 being the least stable, because if you have a charge and you are in sp3, let's say if I had, I don't know, this alkoxide right here, this oxygen is at an sp3 hybridized state, and the electrons are much farther away. They want to be closer at an sp or an sp2 hybridized state. Okay. The other factors that we want to consider is if there's any inductive effects. And the last two is simply like the identity of the atom that's holding the charge, and it will be size and what was it? Electronegativity. And we'll be going over each of these factors as we go along these 6 questions that I drew up on the board. And honestly, a lot of them may be very familiar to you because I did pull them from ALEKS. I see that you guys are struggling with this particular question on ALEKS, so let's go through it. Acid base is pretty hard. So starting off with this one, we have an alcohol right here. And a hydroxide. So we can identify that this is the base and this is the acid. And over here we have the conjugate base, and this is our conjugate acid. And so we want to know, like, okay, which one's who has the charge, or well, if there is any charge right now. And we can see that on both sides an oxygen is holding the charge. So which one's more stable? This actually, I just noticed. So which one is more stable, an alkoxide versus a hydroxide? And we can see that, the oxygen on both atoms are both sp3 hybridization, so we can rule that out. Neither has resonance. It can't really delocalize or share that negative charge or extra lone pair, so we can rule that out. They have the same electronegativity since they're both oxygen and the same size, but nor do they have any inductive effects. So really, the one thing that I can pull off on the top of my head is the electronegativity factor. And we can kind of see that oxygen here is pretty electronegative. It has that lone pair, meaning that it has a lot of electron density. And oxygen is pretty small in size. And that size, right, that small size with those extra lone pairs makes it pretty unstable because lone pairs don't really want to be, or well, electrons don't really want to be next to extra electrons, right? Furthermore, the electronegativity effect withdraws electron density from this carbon towards this oxygen. And so if you think about it, this oxygen is pulling more electron density towards it, more than it can handle. And so this will become a very unstable conjugate base, meaning that the equilibrium will shift towards the left. We always want to know like which side is more unstable. If it's more unstable, then it will push the equilibrium away from it, right? And such is the case right here. We have a protonated ketone here, and an ammonia. On the other side, we have a ketone and just ammonium. This has a plus charge. Okay, so we want to know who is holding the charge. In this case, it's going to be the protonated ketone on the left side, and this ammonium ion on the right side. And so let's look at this ketone here, this protonated ketone. You may wonder, like, yes, there is resonance right here. If I just draw it right here, right. So if we, it's quite small, but if you take a look right here, we can indeed do resonance if we push the electrons here. The only bad thing is that this resonance isn't really going to make it more stable, because you can see that the carbon here is left with 1, 2, 3 valence electrons instead of 4. And so a carbocation is quite unstable, meaning that resonance isn't really going to help its case when we're talking about stability. Let's see. So we identified that there's not really going to be much resonance going on, because if resonance occurs, then it's going to be a lot more unstable. Resonance does count as a stabilizing factor, but in this case, like, we're switching between two high energy states. And so after we consider that, we want to look at who's holding the charge, the nitrogen or this oxygen. Oxygen is much more electronegative, meaning that it would much rather have a negative charge than a positive charge. But nitrogen is less electronegative, so it's much more willing to have that plus charge. And nitrogen, because it has that because nitrogen is less electronegative, it means that it would rather have those hydrogens with it, right? So in this case, the equilibrium will shift to the right. All right, so this one, we have an alcohol and hydrochloric acid, and on the right side, we have a protonated alcohol and chlorine. So many of you have identified, or well, if I were working with you, I would be telling you that this is somewhat of an OChem 2 question, but we can kind of rule it out using our OChem 1 reasoning, right? If we just look at this, hydrochloric acid is pretty strong. The reason being that chlorine is such a big atom that the hydrogen is kind of away from it. Like if I were to draw it right now, then hydrogen is so far away from chlorine that it kind of gives you a clue, like this chlorine does not want that hydrogen, right? It's like it wants to avoid it like the plague, right? And if you kind of look at the periodic table, chlorine is next to the noble gases, and so if you use that reasoning, everybody wants to be a noble gas, they have their full octets. Chlorine wants to be a noble gas, so it would much rather have that those actual lone pairs, hence why it is a strong acid. The size kind of compensates for the extra lone pair. So if we take a step back, look at this again, this is a strong acid, and this is our base in this case, and this is going to be our conjugate acid, and this is going to be our conjugate base. Okay, So as we said, this hydrochloric acid is a strong acid, meaning that the conjugate base must be pretty weak. And if that's the case, then the chlorine does not want the hydrogen again. It's like, no thank you, no thank you. So if this chlorine anion does not want the hydrogen whatsoever, then what is the likelihood that it will accept a proton from this protonated alcohol? Close to none. But this is quite like if we were comparing the stability between the strong acid and conjugate base, this hydrochloric acid wants to become a chlorine so much that it will drive the equilibrium that way. And that's just reasoning it based off of the of the acid here. In other words, we want to look at like who wants to give up the proton more, this hydrochloric acid or this conjugate acid. And we can see that this chlorine in the hydrochloric acid, this wants to give H plus away. Like it really wants to give this hydrogen away. Like it does not want it. This one, on the other hand, it kind of wants to give it away, but like hydrochloric acid really wants to give it away. It wants to be this very stable anion, right? So that is why equilibrium kind of drives it to the right side and not the left. Even if like there's no plus charge, the fact that this is a very strong acid kind of drives it towards the right side. Okay. And so onto the right hand side, we have more questions here. Looking at this. Oh, let me catch my breath. Oh my gosh. Okay, hold on. We want to identify which one's the acid, which one's the base. Here we can see that alcohol is being protonated. So this would tell me that this is the base. And that water here is the acid. Over here we have a conjugate acid. And this hydroxide here is our conjugate base. Okay? And so if we just compare both sides, we have one side that is neutral, and the other side is charged. So this will give us a clue that, okay, that the equilibrium will shift that away to the left. And if we want to reason it by charge, then like hydroxide is a very strong base because it is very small, electronegative, sure, but like that size, the small size will not really compensate for the electron repulsions, right? Neither this oxygen does not really want to be a plus charge. It would rather much be a negative charge because it's electronegative. So based off the electronegativity reasoning, then this would shift towards the left. But honestly, you can kind of just tell right off the bat that this side is uncharged versus this side is quite charged. So having no charges is much more stable. Again, that was not really the reasoning here in this question because we had to pull our reasoning in for this acid here. So be sure to look for those caveats. For this one, we kind of see the same thing as the other question before with the hydrochloric acid. Hydrochloric acid, again, is a strong acid. Chlorine is quite big, meaning that it will handle that lone pair pretty effectively, right? It may not be as electronegative as oxygen, but in this case, the huge size of its atomic radius stabilizes it way more than having it be electronegative. And this nitrogen does have this lone pair that it can accept the proton, and so, oh my gosh, this is going to be the base. Conjugate acid, conjugate base. And so this is kind of the same case, like, okay, who wants to give away the proton more? This strong acid, this hydrochloric acid, or this ammonium, this amine, this protonated amine right here? And the answer is that this acid, this hydrochloric acid, wants to give away that proton way more than this. Nitrogen is okay having that positive charge. It is less electronegative, meaning that it will, it's okay, it's stable with a plus charge, right? It would rather have a lone pair, but if it needs to have a plus charge, then that's okay. But the fact being is that since we have this strong acid, it will kind of push, it will most likely push the, not most likely, it will push the equilibrium to the right side, because like this conjugate base is so weak. This conjugate base is so weak that it will not be plucking off this hydrogen anytime soon. And so this being a strong acid, it kind of just entices the equilibrium to push it to the right. Hopefully that makes sense. Come to office hours if it doesn't, Anyway, and then this last question here, let's see, this carboxylic acid, the name tells us it's going to be an acid, and this is hydroxide, this is going to be a base. We have this carboxylate here, which is going to be our conjugate base. Oh my gosh. Water is going to be our conjugate acid. Okay. Hydroxide, strong base. It has those extra electrons that lone pair of electrons, this extra lone pair of electrons, creates that instability, making this a very strong base. If you see a molecule that is pretty unstable through any means, like this hydroxide here, then it will be a strong base. Same thing with NH2 minus. Nitrogen typically likes having 5 valence electrons. Right now it has 6. And so that extra lone pair is kind of like throwing it off. It's like, I really do not want this lone pair. It's not that electronegative. So it would much rather create a bond to become neutral. Hence, that's why I say if it's pretty unstable, then it's pretty strong, whether it be an acid or a base, right? So back to this question. OH, being a strong base, is going to protonate this carboxylic acid and create this carboxylate. We can see that in the carboxylate here, the oxygen is holding the negative charge, but this oxygen is okay with holding that negative charge because it can do resonance. While over here, this conjugate acid is pretty stable, it's neutral, so it's kind of like saying, okay, which side is better out of the two worst options, kind of. This carboxylic acid, while it is stable, it can accept a negative charge and do resonance, which stabilizes it. This hydroxide can't really do that, so it's kind of unstable, making it a strong base. So the equilibrium will push to the right. It's like saying, okay, who can take care of this negative charge better? Something that can't do resonance and is just localized on one atom versus a molecule that can delocalize and share the negative charge. So the answer is this will shift to the right. Okay? I hope that makes sense. If that doesn't, and if you're quite stuck on it, come see me for workshop hours and or Dr. Ian or whoever for tutoring or other stuff. Okay, good luck. Bye.